Hope you guys are doing well. My name is Adriano Matos. I'm a first-year master's student studying natural resources and environmental science at the University of Nevada, Reno. And today I'm going to be talking to you guys about my research, the GigaFire Project, as it's called, a large-scale fuels mapping and modeling in the cloud computing environment. Before I get into the weeds of the Google technologies that I use, I think it's important first that I talk about some background, how this project came to be, as well as identify some key terms I think are important to discuss so that we're all on the same page. So this project came to be from two agencies, the California Air Resource Board and the California Department of Forestry and Fire Protection. CARB for short is an agency that's dedicated to looking at the harmful effects of air pollution in California. And CAL FIRE is an agency that's dedicated to looking at fire protection in the private wetlands of the state. And both these agencies want to simplify the process of quantifying carbon emissions from specifically fuels treatments. And what are fuels treatments? They're basically ways to be able to make forests more resilient to wildfires. So if you look at the before image here, you see that we have a forest that is densely packed, lots of closely spaced trees, lots of foliage and understory growth below the trees. And if a fire were to come into this area, it would be very intense and very severe. So the idea behind a fuel treatment is that we're essentially converting what you see in the before image to what you see in the after image. And fuels treatments consist of things like thinning, which involves removing trees, mastication, which is another variation of thinning, just using heavy machinery to be able to shred trees down. Prescribed burning and pile burning, which involves fires on the understory to remove all that foliage, to create what you see in this after image, so that when a fire does come into that area, it's less severe and easier to control for firefighters.
You can try to stay this way. The more you move your mouth that way,
Yeah,
so
that's good. Sorry, I tend to move a lot. Okay. Okay, so anyway, sorry. So we want to be able to quantify carbon emissions from these fuel treatments, and we're doing this through a model called the Forest Vegetation Simulator, or FVS for short. It's a forest simulation model. It models forest vegetation change in response to natural succession, disturbance, and management. Essentially, how it works is you pass in tree metrics, things like the species, the diameter at breast height, the age of the tree, site metrics like elevation, slope, and aspect. And then the fuel treatment scenarios. That all goes in together into this model to essentially create these predictions of what these forests will look like after, say, 25 years. So bringing everything together, we want to run this model for the entire state of California for all forested lands. So this formula that I made up basically shows how long it will take to actually run this extent. There's approximately 133 billion meters squared worth of forested lands in California. And each FVS run will consist of a 30 by 30 meter plot, or as I call pixel size here, it's equated to 900 meters squared. I'll be calling FVS runs pixels now, so just to standardize the language. FVS will now be just synonymous to a 30 by 30 meter pixel size. So for each FVS run, we're running 10 treatments and running 100 iterations of those treatments for one FVS run. And then approximately it takes 0.7 CPU seconds to run one FVS instance. And that equates to approximately 29,000 CPU hours. So this is definitely a big data problem. This isn't something that we can run on any ordinary machine. And we need all the computational resources that we can get to be able to run the entire state of California and make it timely. So that's where Google Cloud comes into play. I'm not going to go into everything that Google Cloud has to offer. If I did, I'd be here all day. But essentially, it's a way for users to be able to access Google's virtual resources. It's the same resources that Google uses for things like YouTube and Gmail and Google Search. So the idea here is that we get access to these virtual resources so that we can deploy our applications at any scale that we want to. And now I get into the weeds of the workflow. So I know this might be a little intimidating, but I'm going to break the workflow apart piece by piece and then bring everything together at the end. So we're going to start at the top left and work our way down. So the first step is using Google Earth Engine containerized within a Cloud Run service. So I'm going to explain what those two things mean. Google Earth Engine, for those of you guys who don't know, is a JavaScript/Python API. It lets you analyze geospatial data, and it's free to use. As long as you have a Google account, you have access to this array of data from satellite imagery to weather data to topographic data. Essentially, as long as you have an understanding of programming, you have ways to be able to export this data and do really cool analyses on it. So that's Google Earth Engine, and it's housed within a Cloud Run service. Now, Cloud Run is Google Cloud's flavor of containerization technology. For those of you guys who don't know what like Docker or containerization is, it's basically a way to be able to take your code or your application, as well as all the dependencies and packages that are needed to be able to run that code, and you put it in a box. And by transporting that box to any machine, you don't have to worry about reinstalling those dependencies again and again, or have to deal with version conflicts, which is a common problem with data science and programming languages. So if you take anything out from what I'm saying, Cloud Run is just basically able to let us deploy our own code in the cloud environment. So with that being said, this Google Earth Engine script takes a search area of interest. In this case, it's that small little red square you see within the state of California. We'll eventually run the entire state, but for the time being, we're just running that small square for testing purposes. So we take that search area, and we use that search area as a cookie cutter to extract out pixel values from a data set called tree map. Now, tree map is a 30 by 30 meter gridded data set that was created by the US Forest Service. It represents basically just plot identifiers, and we use these plot IDs to be able to query their database that contains all the tree metrics that we need. So all we're doing is just using that little box and extracting out the pixel values that represent the plot IDs that we're interested in taking in the future. So we take these plot IDs, we'll just look at specifically 980, for example, and we push it over to this next step here where we have a database that contains all the tree metrics that we're interested in. And we're going to use that number 980 here to query that 30 by 30 meter plot for all the trees within that plot to push into FES. So everything that I was mentioning before, species, height, age, all that stuff is extracted in this step. Now we have a compute engine instance, which is just basically a virtual machine. If you don't know what a virtual machine is, it's just a mini computer with its own operating system and hardware. And we have MongoDB installed on this virtual machine. And we have our forest inventory analysis database, which is the database that has all the tree metrics installed within Mongo. So all we're doing here is just simply doing a query for all the tree metrics that we need to be able to run into FES. And then from there, we take all the metrics that we extracted and we go into the bread and butter of the workflow. So it's very similar in the sense that we're still using Cloud Run, but now we have our FES steps. So we're taking the tree metrics in and we're pushing it into our Cloud Run service to generate these predictions of what these trees will look like after applying the field treatment scenarios. Now, the key thing that I want to point out here is that with this Cloud Run service, you'll notice that there's 3 copies of FES. In this case, Cloud Run has a unique feature where you can essentially parallelize your workflow. So each FES instance here is getting its own unique set of inputs. And this allows us to be able to run the entire state of California at a large scale. You're only seeing 3 instances of FES being run here, but right now in our workflow, we can run concurrently up to 1,500 instances of FES, each of which have their own unique inputs. And we can do that within seconds. So we're basically able to generate these products in seconds and make this really, really timely to be able to get this extent that we need to get done. And then lastly, we take those, well, second to last, we take all those forest change products and we just write them into a database. So it's the same technologies that we were using before. We're using Compute Engine to install an instance of Mongo, and we just have an empty database where we just write those outputs into it. And then from there, we can take those outputs and do a geospatial query to be able to create some cool products. Now, in this case, we're more concerned with the carbon emissions. So the raster on the left is just a raster that represents the carbon emissions after applying a fuel treatment scenario. You don't really have to be concerned with exactly what those pixel values mean. It's just a representation of what we can actually generate. But that's basically the gist of the workflow. So to sum it up, from the beginning, we take this search area, we extract out these plot identifiers, we use these plot identifiers to query a database to take the tree metrics that we need for our plots or our pixels. We push that into our FES step. We generate these tree products, and then we write them into a database and then do a query to be able to create cool end products to visualize. So some key takeaways. This project is entirely automated in the Google Cloud space. So as soon as you input in the search area of interest in the beginning, the whole workflow inherently knows how to go from start to finish without any other user input, which is a really nice feature. We can also spatialize FES. FES doesn't have an inherent idea of where the trees are located. So by using this tree map data set, I don't really have to go back at this point, but by using the tree map data set and the search area of interest, we can essentially identify any area that we're interested in and create these products based upon, again, whatever search area that we're interested in. We can externalize geospatial analysis outside the scope of Google Earth Engine Google Earth Engine is great. The fact that it's free to use for any user is astounding, but we are limited in the sense that it is a shared resource. So by being able to use what cloud has to offer, we can take what Google Earth Engine gives us and go even further beyond. As I mentioned before, this project runs the applications in parallel. That's why I was shown before with the FES step. And lastly, we can generate spatially explicit uncertainties for all FES outputs. So I mentioned briefly before, and you guys probably don't remember, this iteration part. So for a single pixel, a single 30 by 30 meter section of trees that we're interested in looking at, we're actually doing a sample of those trees within that same area 100 times. And what that allows us to do is essentially we can take the variance of those iterations and create uncertainty maps to be able to make sure that we have an honest prediction of whether or not these forest change products are accurate. So the next steps would be to optimize the computational efficiency of our code to save costs. Despite the fact that it works really well and it's really fast, it is pricey. So we're working on trying to port over the workflow to our own high performance computing environment at our university to be able to save some money. So it's one disadvantage, it is costly, but at the same time, it's a really great resource to be able to create these products in a fast way. The visualization step is technically not incorporated into the workflow just yet. We are just at the stage where we have all the outputs written in the database and we mainly just do the query ourselves. That will eventually be incorporated into the workflow and will be automated. And then the tree map raster, the raster that we use to be able to grab the plot IDs that we need to be able to do the query to take out those tree metrics, that will actually be replaced entirely with a generate synthetic tree list at every position within our search area. That's where the 100 iteration part comes into play. That will make things a lot easier for us to be able to create those uncertainty maps. And yeah, that's basically it. My poster session is tomorrow. So if you guys have any other questions, feel free to bother me or pick my brain with whatever questions you may have. Now, this project was also a collaborative effort. I was in charge of just programming it and putting it up into the cloud space. But if you have any questions regarding synthetic tree lists or uncertainty, my colleague Taylor Brown, she unfortunately had her poster session on Monday, but she'd be more than happy to answer questions regarding synthetic tree lists. And then my other colleague, Ashley Kale, she was in charge of the whole FES process. I basically just ported it over into the cloud space. But if you have any questions about how FES works and how you actually define the field treatments and how to actually push in the inputs, her poster session is tomorrow afternoon, and she was directly involved in this project. So she'll know everything that I'm talking about. So feel free to bother her with specific questions regarding FES if you have them. And that's basically it. Just want to acknowledge all my colleagues at the lab who helped me make this project possible, as well as a couple of Google engineers, Yvonne Aquino and Payam Musavi, who are customer engineers at Google, who gave me a lot of insight on how to be able to parallelize this workflow. And that's it.